So, we did some practice with calculating magnetic field due to a long straight wire using cylindrical coordinates. That was my main agenda in the previous lecture. We will continue with that with another simple example that you had done in school days, and that is magnetic field at a point, magnetic field due to a circular current at a point at the axis of this circular loop. So, essentially we have a circular loop, and in that circular loop we assume that we have a current, and then here is the center of the loop, and this is the perpendicular, this is the axis of the loop, and on this axis there is some point P at a certain distance, let us say r, from the center of this current, and here we need magnetic field because of this. So, this time we will set up our coordinate system, and the coordinate system will be that on this in the plane of this loop we will take x axis, y axis. So, let us say this is x axis, this is y axis. X axis is coming out of the board, is a 3-dimensional figure that I am trying to draw here. So, this is in the plane, this is z axis, this is z axis, this is y axis, and the x axis is coming out of the board. Half the loop is on our side, classroom side, and half the loop is back side. So, if I draw this itself in xy plane, the wire is like this, the current is like this, and then you have this current, and then there is an axis that we will be drawing a dashed line. So, this is not in the plane of the board, the axis is perpendicular to the board, and on the axis, at some point on the axis we have this point P where the field is needed. So, we have our x axis, we have our y axis, and so on. To take current element on this loop, our process will be that we will use cylindrical coordinate system, and let us take a point here on this loop, at point here, then this angle is phi, cylindrical coordinate phi. This length which is fixed here, the radius of the loop, say suppose the radius of the loop is a, then this length is s is same as this a. For this point, what is s coordinate? What is s coordinate? Drop a perpendicular on the z axis, and that will meet here. So, this length is a. If you want to draw the unit vector s cap, it will be in this direction. So, this is phi. Then we increase this phi to phi plus d phi, we reach somewhere here, this angle is d phi, and then this is our current element, this will be our element, and this will be s times d phi, that is a times d phi, this length, because of this current, this is our dl vector, because of which we will be writing magnetic field there using Biot-Savart law. So, if I say that this is our point P and this is the origin O, so this is OP vector, and this OP vector will be A times S cap. This is OP vector. Let us call it A, let us call it point A. So, OA vector is small a times this S cap. P point is here on the axis, What is the coordinate of that? This OP vector will be capital R times k cap, and OA vector is small a times S cap. What is the vector A to P? This vector A to P, Why I am interested A to P? Because in Bart-Savart law I will be writing dB equal to mu naught over 4 pi I dl cross r by r cube, and this r vector is from the current element to the point where field is needed. Here is the current element at A, current element is at A, somewhere here, let us say here, this is our current element, this point is A, and then the field point where the field is needed is here P. From the current element to the point where field is needed, that will be AP. That is why I am interested in writing this AP, and that is why I am doing all this exercise. So AP will be AO and plus OP, and AO will be negative of OA, so it will be minus AS cap, and OP vector is RK cap, so plus RK cap. This is that this R vector. So what is the magnetic field at this point due to this current element? It is mu naught over 4 pi, and then I here dl. What is dl? This is dl. What is the magnitude of dl? The magnitude of dl is AD phi, length. This is the length. What is this direction? We are turning like this parallel to the xy plane. That is our phi cap direction. Phi is increasing. This is phi. The phi is increasing. It is phi cap direction. So this is phi cap direction. That is dl vector. So I and then dl vector cross this R vector, this AP, from the current element to the point where field is needed. So that AP, that will be minus AS cap and plus RK cap divided by R cube, and R is the length from the current element to the point, and that means magnitude of this AP vector, it is here, and that R is the square root of, remember these are perpendicular directions, S cap and K cap, so it is A square plus R square. So A square plus R square, and 3 by 2 of this, so it will be A square plus R square and then 3 by 2. This is the magnetic field due to this small element here at this point P, and we want the magnetic field due to this entire loop, and therefore we have to integrate so that all parts on the loop are covered. And if you see it here, that means this phi should go from 0 to 2 pi, so that all current elements like this here, everything is covered. So if I vary this phi from 0 to 2 pi, then all this will be covered. So first let us simplify this. This is mu naught I by 4 pi, mu naught I by 4 pi. Then we have this A d phi, A d phi, phi cap cross S cap, phi cap cross S cap. This is the sequence S, phi and Z. So phi cap and cross S cap, so opposite. So this will be minus of Z cap, right? S cap cross phi cap, S cap cross phi cap is equal to Z cap, which is K cap, and therefore phi cap cross S cap will be minus of K cap, another minus is here. So this will be A times K cap here, A times K cap, phi cap cross S cap with a negative sign is this K cap. Then here plus A d phi we have already written. So phi cap cross K cap, phi cap and then cross K cap will be S cap, phi cap cross k cap will be S cap, S cap. So, this is S cap, S cap. A k cap and plus R S cap. Right, what we are writing, this A d phi is here, phi cap cross this vector that we are writing here, and we get A k cap and plus R and then S cap divided by A square plus R square 3 by 2. Integration, integrate, what is B? What is B? So, integrate. Mu naught I by 4 pi is a constant, mu naught I by 4 pi is a constant. Then A square plus R square, this is also constant. A is the radius of the loop and R is the distance from the origin to the point where you have to find the field. So, this is also constant, A square plus R square 3 by 2. Then what is left? This A also, if you wish, you can take it here, this A can be taken here, and then we have two parts. One part is A d phi k cap. So, A d phi k cap, this is to be integrated, this is to be integrated. Then other part is R d phi s cap, R d phi s cap. So, plus R d phi and s cap. This is the integration, and rest of it we have already written. So, let us take the two integration one by one. This is A and d phi, let me write k cap here and then d phi. Now, in this k cap is constant, k cap vector is constant, it is vector, unit vector along the z axis. Z axis is not going to change whether you take the element here or here or here or here. So, this is constant, it does not depend on which phi you are talking of. So, this is equal to k cap outside A d phi, and this is equal to k cap, then A is constant, d phi integration is 2 pi. So, 2 pi A. So, this is 1. Okay. The other integration is capital R d phi and s cap, you write it R s cap and d phi. R is constant, you can take it out, but s cap is not constant. S cap is not constant, depends what phi I am taking. If I am taking phi here, if I am taking phi here, if this is the point, here is the element, then s cap is this is s cap. If my element goes here, I have to take all the elements, remember phi changing from 0 to 2 pi. So, if my element is here, then s cap vector is this one, this is s cap vector. If the element is here, then s cap vector is this is that s cap vector. So, this s cap vector keeps changing as you change phi from 0 to 2 pi, and therefore, this you cannot take out, and if you add all these s cap vectors, if you add all these s cap vectors, s cap into d phi, s cap into d phi, s cap into d phi, s cap into d phi. So, if you take all the d phi equal and take it common, you are just adding all these s cap vectors, and this addition is 0. this addition is 0 because you are adding all this, what this vector, 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 all these vectors you are adding, and that vector sum is 0. So, this part is 0, this part is 0. What is B then? What is B then? B is mu naught I A by 4 pi A square plus R square 3 by 2. This part is 0 and this part is k cap 2 pi A. So, 2 pi A and k cap. This is the final magnetic field, and this 2 pi and this 4 pi you can write 2 here, then this A and this A will be A square. So, mu naught I A square, mu naught I A and this A, this 2 pi and this 4 pi is 2 A square plus R square 3 by 2 and then k cap. This is your answer. So, answer is anyway, you know, you have derived it, you have used it several times in your class 2. The important point I wanted to do in this lecture was how to deal with these vectors in cylindrical polar coordinates. We are using this k cap, which is common in Cartesian and in this thing cylindrical, but S phi z, that system I wanted you to be more familiar with, because later you will be using this system quite frequently. And if you take this capital R to be 0, this capital R to be 0, you are at the center of the loop. So, the magnetic field due to a circular current at its center, that also you can write from here by just putting this capital R as 0, and this will be at the center of the loop. It will be mu naught B will be equal to mu naught I A square divided by 2 and then A square 3 by 2 power here. So, it will be A cube, this is 0. So, it will be A cube, and that is equal to, this will be A mu naught I divided by 2A. That is the magnetic field at the center of the current loop. Analytically we are not able to derive such equations for points which are off the axis, right. We have talked of magnetic field at a point on the axis and as a special case at the center of the coil. But what is the magnetic field here? What is the magnetic field here, 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 or here, or here? For that it is possibly we will not be able to write such simple equations for that, but we can always do the integrations on computer. These are standard formulae that we have used for integration, but then there are programs where any kind of functions you give, if it is possible to have the integration, numerically computer will do it and give you value. You have to feed the numbers and then the computer will give you value, this component, x component, y component, and you can combine and write it. But qualitatively we know at least the direction or pattern of directions which are represented by the magnetic field lines. So, if you have a loop here, current carrying loop, and this is that plane, then everywhere on this plane of the loop the magnetic field lines will be going perpendicularly everywhere, everywhere. It will be starting like this, and then as you go away, then you will have varieties of lines. This line will go this way, and on this side it will go this way. So, it will come like this. If you are close to this here, close to the wire, then possibly it will go and it will turn here, okay, like this, similar thing on this side, similar to central one will be of course straight, one will be straight, and then you will have lines like this. Then if you are close enough, then the lines will be like this. It will turn here and then come back like this. So, this kind of pattern, which is very important to know, because we need magnetic field. If you are doing some practical applications, you need magnetic field everywhere. So, this is how it goes here. Now, interestingly, we had seen that if the current is in z direction, the magnetic field is in phi direction. So, the magnetic field lines, if you draw, this will be like this. These are B lines, and here we are telling that this is the current. So, the current is in z direction and B lines are in phi direction, and you can use this right hand thumb rule, that your thumb is along the current and then the fingers are curling in this these directions. These are the directions. You can draw lines here. So, you can have lines here, you can have lines here, you will have lines here, you will have lines here, and so on. Anyway, and the thing which we just did is that the current is like this. The current is like this. The current is going in phi cap direction. So, current is along the these fingers, if you do that way, and the field here at the center and at the points, the field is in this direction. So, field B lines this way. Again you can use that same rule. If you curl your fingers, along the current, then thumb gives the magnetic field. If you put thumb along the current, then the fingers give you the magnetic field. So, this is a relationship which is interesting and easy to remember, that if the current is given, you curl your fingers and your thumb will give this. If the current is given to be straight, then your thumb is straight, put thumb there, and then the fingers will give you the B lines. So, these are the kind of things which you can derive from all this discussion.